Basu is currently an associate professor at the Theoretical Statistics and Mathematics Unit of ISI Kolkata. He has earned his PhD degree in mathematics from Harvard University under the supervision of Professor Michael Hopkins. Prior to his joining ISI as a faculty, he served as an assistant professor at Ramakrishna Mission Vivekananda University, Belur. His primary research interest lies in algebraic topology and homotopic theory, specifically in topics namely equivariant cohomology, stable homotopic theory, and duality phenomena in topology and algebra. He has authored several research papers including works on Redon cohomology and computations on cyclic groups over prime power orders. Besides teaching and research, he has mentored PhD students and has also co-organized national-level mathematics workshops such as the Duality in Topology and Algebra workshops at ICTS Bangalore. Now, I request Sir to share his invaluable insights with us.
Okay, so শুরু করার আগে first of all I should thank Prof and others in the mathematics department who invited me for this event, and special thanks goes to the students for organizing something like this, because I heard that most of the event is being organized by them. And so let me now go ahead straight into my lecture. So my field of research is in topology, and if you try to understand the area of topology as a subject in mathematics, you would say that it's fair to say that topology is a subject which was born out of mathematics in general. So unlike other subjects like for example analysis, so differential calculus for example was formed in order to make sense of ideas of speed and acceleration and laws of mechanics and so on. But what if you think of geometry was formed to understand natural ideas of curvature and things like that. But it is fair to say that topology is a field which came up to understand questions which arose from mathematics itself. So unlike say subjects like number theory, which you will see after lunch, number theory is something which is very old, more than 2000 years, or geometry, which is also quite old. Topology is a subject which is relatively new. It's only maybe a couple of 100 years old, and that's why I think it isn't usually part of the undergraduate syllabus in most of the universities. But today, so what I want to say is that how do you build up ideas in mathematics? Well, you make some observations and then you try to explain it in very rigorous terms, So that's, you want to write something which will be true no matter what. That is very important in mathematics, that you want to say that something is true no matter what. So for doing that, you need to develop some axioms and some, you have to make suitable definitions, and you have to write a proof which will not be, which will stand the test of time. So broadly, if that is the way the mathematics is developed, what I want to show you is, even in topology, there are certain very natural kind of curious phenomena which arises, which somehow to answer them, it leads you directly into topology, or more specifically algebraic topology. And my lecture is broadly going to be about that. So I will talk about this belt trick, which is a kind of a curious thing, which I think anyone who wears a belt would have observed at some point. And then I will tell you why, if you want to make it rigorous, why ideas in topology are very important. So that is the main idea of this lecture. So the point here is that I want to, so you would see that when you wear a belt, sometimes you would get sometimes the belt twists, and then you cannot untwist it when it is closed. But if you have twisted it twice, then often you are able to untwist it. So that is the idea which I want to show here. So if suppose you keep the top end of a belt fixed and rotate the bottom end in a circle around it, so it looks like this. So there is a twist, and if you keep the top and the bottom fixed, there is no way in which you can make it straight. I think many of you would have tried something like this, but there is no way. And so this is what we are trying to do. We deform this twisted belt, keeping the ends fixed. So that means this is what we are trying to do. So we are keeping the top and the bottom fixed, and then we are deforming it. So this twisted thing will look like, or will look also like going around the bottom and coming back on the top. It's also, if you deform it, this is also another picture which appears. And now you see, you can also move the left hand side on top of the diagram, and then you get the opposite twisting. Yeah? And however you try, you cannot get this straight. Okay? So you observe that whatever ways you try this, you observe that the twisted belt cannot be untwisted with these transformations. So this is the idea, but just trying and not being able to untwist it is not good enough for us from the point of view of mathematics. So you want to know for sure that that there is no very exotic way which you have missed, right? So if you want to say that this will not happen, like as a mathematician, you would want to rule out all the possibilities that can exist. And the possibilities could be, there are of course infinitely many possibilities, so you cannot have tried all of them in a finite time. So you need some way of saying it. Okay? So now so this is another thing which I said, if you twist it around twice, so if you rotate the bottom end one more time, then what happens? Then you have this kind of double twisted gadget. Now the double twisted gadget, this is the deformation which we had in the previous slide, that it goes around the bottom and comes on the top. And then I said so I said you go around the bottom and come on the top, and then you see that in the difference between the third picture and the first picture is that the strand in the middle, which is this one, see in this one it goes below. On the left it goes below, but on the right it goes above. So it is actually the straight one with some perturbations like this. So that can be straightened down. Okay? So what I said, if you twist it once, then it cannot be straightened. You can try and it cannot be straightened. But if you twist it twice, then it can be straightened down. So the twice rotated bed can be transformed into the untwisted bed, while the once rotated bed cannot. And this is what I will call the bed truth. Okay? And this is what I want to understand. So I want to say why the once rotated bed cannot be twisted and made straight. So I have to give you, so what I want to do is I want to give you a mathematical proof of this fact that this cannot be straightened. Alright? This is the main point of the lecture. So you might be wondering that, okay, this is just, so this is the kind of thing which we do in mathematics. It's like now I asked a question which it seems that, okay, it is very clear. But if you think about it from a mathematical point of view, as I said, there are infinitely many ways in which you can move the bed around, and because the topic of this event is also infinity, so you would know that this cannot be, whatever finitely many steps you do in a finite amount of time, it is not good enough to rule out infinitely many possibilities. So you need something else. Also, there are results in mathematics which do not appear to be true in plain sight, but which is actually true. So, for example, there is this Banach-Tarski paradox, which says that if you are given a sphere, like the surface of a ball, then you can cut it out and then join it back again, so that you get two balls of the same volume. So this kind of thing, you wouldn't be able to do it in practice, because what it involves is a lot of you have to cut it along various, you have to cut it along irrational positions. So you cannot do it in practice. So if you were trying to see whether it is possible and you keep on doing it, you will never be able to do it. But mathematically it is possible. So it is just saying that you are not being able to do it is not good enough from the point of view of mathematics. You have to rule it out by some proof. And this is exactly the kind of place where topology enters, and it gives you a way of proving results like this. So what you need is something like an invariant. So you need some kind of invariant which is not equal to 0 when you take the once twisted bed, and which is equal to 0 in the double twisted bed. And whatever this deformation that we are doing, that keeps the invariant same. This is what you want to do. So this kind of thing, say for example, where else do you need invariant? So suppose you wanted to say that the line, the real line, is it equal to, can you identify it continuously with the plane? Then I guess many of you would have known why that is true. So if you remove a point from both the things, the real line separates into two disjoint parts, two different parts, while the plane you can draw a path from one point to the other if you remove a point. So that will tell you that the real line can never be continuously identified with the plane. So like this kind of number of components of a geometric shape, this is like an invariant. And this kind of careful study of invariance is what algebraic topology is about. And in this case, this is what we need, and that's what we are going to do. So we need to understand. So in order to understand this belt trick, you have to consider transformations like this, where you are deforming this belt, keeping the top and the bottom same, top and the bottom fixed. So these are precisely the rigid twists that preserves the two ends. And as I said, you need to construct an appropriate invariant. Invariant means there is this rigid process that we are doing, and the invariant should be preserved throughout this process. That's what. Okay? Good. So let's go ahead. So you need to construct an appropriate invariant, and that's what we are doing. So you look at the center line of the belt, and when you are looking at the center line, the belt, there is one direction which is going up, and then there is a one which is the perpendicular direction. So you can draw two vectors, two perpendicular vectors along the plane of the belt, like this. So this is the twisted guy, the twisted belt. So you have, so there is the red vector goes along the belt in the direction up, and the blue vector is the one which goes horizontally along the belt. Okay? So you consider two perpendicular vectors along the plane of the belt. And for every belt configuration, therefore, you get an interval of pairs of vectors in space, which is R3, that varies continuously. Okay? So the interval I is you can think of as the closed interval 0, 1. So you have pairs of perpendicular. So for every so you think of this belt as a closed interval 0, 1, okay? So the center line is like a closed interval 0, 1. And for every point on this center line, you have this pair of perpendicular vectors in R3. Right? Given the configuration, you have this pair of perpendicular vectors. And these vary continuously because if you are close enough, it's like this kind of a square shape, so it is. So you have a function like this, from belt configurations to maps. By map here, I mean a continuous function. Okay, so it's just the word we use. Map means continuous function. And function means something is a function which is not necessarily continuous. So maps from I is again the closed interval 0, 1, to pairs of perpendicular vectors in R3 with the same value at 0 and 1. See, 0 and 1 has the same value because it's fixed with that kind of orientation, so it will get the same value. Because the bottom and the top are fixed. Okay. So you get a map from belt configurations to maps from I to perpendicular vectors. Well, if you look at the set of all functions continuous functions from 0, 1 to R3 to perpendicular vectors in R3, this is a very large object. It's not something which is very easy to write down, but this is going to help us. Okay. So let's see. So now I will define a geometric object which is going to be useful for us. So you look at, I will write V1 to be the set of unit vectors in R3. Okay? So V1 as an object, how does it look like? A unit vector in R3 gives you a point on the sphere inside R3. So the sphere is like the boundary of the ball. Okay? So the sphere we write as S2. S2, the 2 on top stands for the dimension. The sphere is inherently a two-dimensional object. You can only move on the surface. There is a normal direction which is going outside. So the set of unit vectors in R3 is the sphere. We call this the 2 sphere. And so this is the space. But now I am not happy with just unit vector in R3. I need pair of perpendicular unit vectors. So this is not exactly the geometric object, but first thing that you start with is this. So this is how S2 looks like. This is the boundary of this ball, which is colored blue. The boundary of that is this. Okay? So you see, this is, if you have not seen the definition of topological space, it is okay, but you probably know what open sets are. So topological space is the idea of, like, if you know what a metric is. So metric is something which can measure distances, but a metric allows you to define open sets. But now topological space is something which is just determined by the collection of open sets. So the main important property of a topological space is continuous functions, and you know continuous functions can deform distances in a very bad way. So if you want to say that they are identified continuously, then you know a small sphere is also identifiable with a large sphere. But if you want to preserve distances, then it wouldn't be the case because the perimeter would have to be equal. Or, sorry, the surface area would have to be equal. That doesn't happen. Continuous maps can change this surface area. They can change distances. So that's that's just what I want to say. But this is even better. This is actually, there is this metric which comes from R3. So in R3 you can calculate the distance between points. So that makes S2 a metric space and hence a topological space. Now let's go to the thing which we actually want, which is V2. V2 is the pairs of perpendicular unit vectors in R3. Okay? So that is U comma V belonging to R3 cross R3 with mod U equal to 1, mod V equal to 1 and U dot V equal to 0. Now R3 cross R3 is again, it has a metric. R3 cross R3 is 6-dimensional Euclidean space. So that also has a metric. And inside that metric you can talk of distances between 2 points in V2. So this V2 also is a topological space. So that's what I am writing here. This gets a topology as a subset of R3 cross R3. So you can measure distances in R3 cross R3 and that makes V2 a topological space. Okay? Now, so now we have gotten to the point where we are interested in is this V2. So remember in the previous slide we had maps from I to pairs of perpendicular vectors in R3 with the same value at 0 and 1. So now you can say we get maps from I to V2 with the same value at 0 and 1. That's what we do. Okay? So continuous functions from I to V2. But V2 I want to understand a little bit better. So if you are now, suppose you are given a point in V2. I want to identify it with a topological space which is more useful for us. So you take u comma v, a point in V2, and given a pair of perpendicular vectors in R3, you can get the cross product, which is perpendicular to the first and the second. And the cross product has the property that you have, so if you have two unit vectors and you take the which are perpendicular and you take the cross product of that, then these three vectors forms the orientable frame in R3. This is something which we know, right? Orientable frame is determined by this right hand rule, which you would have learned in school. So you get a oriented three frame in R3, u comma v comma u cross v, which is given this right handed orientation. Okay. Now, if you know a little bit of linear algebra, you know how to identify oriented three frames using matrices. See, if you are given perpendicular vectors and you write them as column vectors in R3, right? So you get a 3 cross 3 matrix, but it's not just a matrix. These vectors are orthogonal, so you get an orthogonal matrix. And what the thing that you are getting here has right-handed has the correct orientation. So inside orthogonal matrices, you have determinant 1 and minus 1. So these are the guys which have determinant 1. So that is a special kind of matrix. It's called a special orthogonal matrix, and this is denoted by SO3. This is what I am writing now. Therefore, V2 is the same as oriented three frames, u, v, u cross v in that form. And for each oriented three frame, you form the matrix with the corresponding vectors as columns. This is an orthogonal matrix of determinant 1, as I said. Because the columns are orthogonal and they are oriented, so that means the determinant will be 1. The set of these matrices is called SO3. Okay? So you have an identification between V2 and SO3. So see, I am not losing my focus on the original problem. I have to build up this invariant, which I am going to be talking about. And for building up the invariant, I have this map from closed interval 0, 1 to pairs of perpendicular vectors. But now I have reduced the formulation to this SO3, and SO3 is supposed to be, these are just matrices, so they are easier to work. That's the way we think about it. Okay? Good. So now I will understand SO3 a little bit better. So, but SO3 fits into this family SON for every n. And if you have learned a little bit of linear algebra, then SO2 you know is identified with the circle. The matrices in SO2, that means the pairs of two orthogonal vectors which have the correct orientation, then these matrices are all of the form cos theta, sin theta, minus sin theta, cos theta. This is something which you can work out very easily. And this matrix is like, if you view it as a transformation from R2 to R2, this is just rotation by angle theta. So a 2 cross 2 orthogonal matrix of determinant 1 is just a rotation. So this implies that SO2 is the circle S1. It's identified with the circle inside R. So now we have, see, SO2 is circle. Circle is something which is friendlier for us. So now I am slowly I'm making some identification so that I can, this B2 is something which is more manageable for our perspective. So SO2 is the circle. What about SO3? So how do you understand SO3? So SO3 is a 3 cross 3 matrix, 3 cross 3 orthogonal matrix of determinant 1. Well, one property of a 3 cross 3 real matrix is that it will always have a real eigenvalue. Right? You get a characteristic polynomial is a degree 3 polynomial, and degree 3 polynomial, real polynomial has a real 0. So there is a real eigenvalue. So there is a real eigenvalue means there is a real eigenvector. So every matrix in SO3 has a real eigenvector. So what does it mean to have an eigenvector? So in SO3 it will be, so that vector will either be taken to that itself or minus of that, and the other and because it's an orthogonal transformation, the perpendicular space, it will act as a rotation. So that's what I want to say here. So any 3 cross 3 orthogonal matrix of determinant 1 fixes a vector B, and yeah, you can check that 1 is an eigenvalue because the other two eigenvalues are complex conjugate. So if you multiply them, then their product is positive. So if the determinant has to be 1, this cannot be minus 1, it has to be 1. So it has 1 as an eigenvalue, and you have a vector B. So now you consider a ball of radius pi in R3, and so for V you have this matrix. So V is a element in that ball of radius pi. So using V you can form this matrix which fixes V and rotates the perpendicular frame by the angle which is given by the magnitude of V. Okay. So that gives you all the matrices in SO3 by the line which I had written before. So this gives you all the matrices in SO3. So you get a surjective map from this closed ball of radius pi to SO3. But this map is not injective because, of course, if you take the 0 point, then it will go to if you take V and minus V, then it goes to the same point on the boundary. So, yeah, that's the statement here. You note that phi of V is minus V. So, and then there is no other identifications. So, what you get is that SO3 is now identified with this ball of radius pi. Mod V is identified with minus V on the boundary of the ball. Now this space is called the 3-dimensional real projective space, or RP3. Okay, maybe it's a little away from what you have learned so far, but you can see that this is roughly this is what. But the thing in the middle is the one which will help us. You have a ball of radius pi and you have identified V and minus V. Okay. So this is the set of perpendicular vectors inside R3. Is this ball is a closed ball, and V and minus V are identified on the boundary. That's what it is. Alright, so we have identified that, but now I have to think about maps from I to that. Maps from close 0, 1 to that, where the value at 0 and value at 1 are the same. So we have to think about that. Alright, so let's think about that. and try to get an integral. So a bed configuration yields a map gamma from I to V2 such that gamma of 0 equal to gamma of 1. So this is called a loop, right? Because the starting point and ending point is the same. So the picture looks like a loop. So this is called a loop. So you get a function from bed configurations to loops inside V2, which is same as the loops inside SO3, which is same as the loops inside RP3, and this is what I defined all with V and minus V identified on the bomb code. Okay, so now starting from loops we define an invariant. Okay, so suppose X is a topological space. If you don't know the definition of topological space, it's okay. You can think of a metric space. So it's a metric space, so you know how to define continuous functions onto that. So suppose X is a topological space. A loop in X is a map gamma from I to X such that gamma of 0 is equal to gamma of 1. This is exactly what we are talking about. And this is how it looks like. So suppose this is the picture of X and gamma will look like this. So there is a point which I have not denoted, which will be gamma of 0 and which is equal to gamma of 1. So that is going to be a point on this green loop. Or this is another topological space. This is called a torus. This X is called a torus. So you can think of this is like the surface of a tire inside R3. So this is the torus and this is the loop on the torus, this gamma, the green one. Now this is the key definition. Two loops gamma and gamma prime are said to be homotopic if there is a continuous deformation from gamma to gamma prime. So continuously you should be able to deform one loop to the other loop. Then they are said to be homotopic. Okay? So here this is the picture. Gamma is homotopic to gamma prime. There you can see you can continuously move the yellow loop to the green one. That's something. This is another picture. Gamma is homotopic to gamma prime. You see that yellow loop, you can just push it and it becomes homotopic. But if you take this one, gamma double prime, which goes in the other around the other circle in the torus, that is not going to be homotopic to gamma. Well, there is a proof of that, but I don't have time to prove things like that. But it's not obvious from the picture that this is. Okay, so roughly this is the thing, and you want to study. So this being homotopic, that means continuously deforming one loop to the other, this is an equivalence relation and you want to study the equivalence classes. Okay? That's what you want to do. So this is an equivalence relation, you want to study the equivalence classes. Well, the equivalence classes you want to study. Now the key thing is, so far I have only talked about topology, but I said that these invariants naturally lead us to algebraic topology, and this is where algebra enters into the picture. That when you take these loops up to homotopy, these equivalence classes has an algebraic structure. Namely, this has a group structure. So if you have studied group theory, you would be able to relate to this point. So you take a topological space and a point in X. Now you define pi1 of x comma x, which is the loop starting and ending at x. That is gamma of 0 equal to gamma of 1 equal to x, and the relation is homotopy which fixes x. So keeps x fixed throughout the deformation. Now, when you do that, you see elements of pi1 of x can be pi 1 of x comma x can be multiplied like this. So if you have this point x, you have a and a b. Now you can first go along a and then along b. So if you want to write the map here, you have say gamma, you have alpha, you have a is the green loop and b is the yellow loop, and you go along a for half of the time and then you go along b for the second half of the time. So that is what I am writing here. A times b is the loop a followed by the loop b, and this is roughly another copy which is homotopy to this loop. And then one has to check all the details that with this multiplication pi 1 of x comma x becomes a group. Well, what is the identity? Identity is the constant loop. That means gamma is equal, gamma of t equal to x for all t. And the inverse is just to go along the same loop in the opposite direction. That is the inverse. And this makes the pi 1 of x a group. So this is an example. X is the circle and small x is any point in S1. So, okay, I couldn't draw this part of the circle, but you can understand what is happening here. You are going around in the anti-clockwise direction starting from x and then you come back and to x. Okay, so basically you have to think of this picture inside the circle, but it's hard to draw that because the whole circle will be green here. But yeah, so this is roughly the picture of the loop. So this loop is homotopic to the circle thought of as a loop. That means you just go around once around the circle. It's homotopic to that one. In fact, two loops are homotopic if and only if they wind around the circle the same number of times in the same direction. That's the result. So if you were doing a topology course, this result would come right at the end of the semester. So it requires some work to prove this. Okay, but roughly you see now you have this loops up to homotopy, and they are and you can say when loops are homotopic or not. But our interest is in that space RP3, which is the closed ball with V and minus V identified on the boundary. Okay, so this will actually say that pi 1 of S1 comma x is Z, is the group Z of integers. Okay, so what about RP3? So we have seen the map which starts from belt configurations to loops in RP3, and a deformation of belt configurations leads to a homotopy of the corresponding loops. So now this gives you an invariant from belt configurations to pi 1 of RP3 comma x, where x is some fixed point. Okay. So if my pi 1 of RP3 is not 0, and if I show that for the configuration with one twist, it goes to something which is not 0. See, clearly the straight bed goes to the constant one, right? Because all the vectors are the same. The straight bed goes to the identity element. But if I can show that the once twisted bed doesn't go to the identity, that means the right hand side is not 0 and it doesn't go to the identity, then that's a mathematical proof. Okay? And that's what I will try to point out. So again recall RP3, now we are thinking about it topologically, so it doesn't matter what the radius is, you just take some radius r, and so you take the ball, closed ball, and b and minus b you are identifying on the boundary. Okay, so this is your closed ball. Now any loop in RP3 can be homotope to miss an interior point. So there is one point. So this loop is a one-dimensional object. You can make it miss a point inside the interior of the loop. So there is an argument for that, but it's not very hard. So such a loop, if you can do this, so you can extend it radially and you go to the boundary, which is the sphere. Now the boundary is a two-dimensional object. Yeah? So again, you can apply the same argument there on the boundary, and you can make it miss a point, and then you can homotope it down to the equator. So if it misses a point, then you just go down to the equator. Okay? The image of the equator in RP3 is of the form the circle mod x equal to minus x. This is also like a circle inside RP3. The corresponding loop alpha in RP3 is the boundary of the disk, which is the image of the sphere. And this alpha is, what I mean is that you look at S1, okay? And now you are looking at x equal to minus x. So inside RP3, half circle goes and winds around as like a loop. But then you are doing minus x, so you are again going back. So this is going to be homotopic to a constant inside RP3. Not inside S1, but inside S1, but when you go to RP3. So because it's the boundary of a disk, right? Image of the upper hemisphere. But there is another loop in RP3 where you go around half the circle. See, S1 mod x equal to minus x. That means minus 1 and 1 are identified in RP3. So if you go from 1 to minus 1 along half the arc, along the half arc, then that will give a loop inside RP3. So the image of the half circle in RP3 is a loop beta as the endpoints map to the same point. This cannot be homotopic. So this cannot be homotopic to a constant. That is the result. And you also know that alpha equal to beta times. So that this is kind of roughly the idea which I am telling you. Again, this proof that pi1 of RP3 is the group of integers modulo 2, Z2. This also requires some work, so you have to develop pi1, you have to make a proper definition, and then you have to do some technology at the end. But again, this kind of thing you can roughly, if you take a semester's course in topology, you can get to it at the end of the course. This kind of thing. Okay? So you have pi1 of RP3 is Z2, and you know the non-trivial element here is the loop which goes around half the circle. So we have this invariant from belt configurations to pi1 of RP3, and now we can compute this. So in this once twisted belt, what does it look like? This will go to beta inside pi1 of RP3. So you can compute it, and you can see that this will go to beta. So this is a non-trivial element, and that's what so that shows that this gives you an invariant, and it's non-zero. So that means this configuration cannot be deformed to the straight. But if you now take the double twisted one, then you can cut it at the half. So if you cut it at the half point, then that's alpha, and then the next one is also alpha. So it's alpha times alpha. But the group is Z mod 2, Z2. So if you take alpha times alpha, that is 0. So that is beta times beta, that is 0. That is equal to alpha, which is trivial. So that shows that the same invariant does not say that double twisted one is trivial, but we know that double twisted one can be straightened out. Okay? So that brings me to the end of my lecture. So as I promised, I showed that this single twisted belt cannot be straightened out, and using this invariant. So we now talk a little bit about some invariants in like this is one of the basic constructions in algebraic topology, which is used to explain some natural fact which you would have been seeing many times. So I will stop here and thank you for attention.